Hello, everyone, and welcome to the Standard and CUDA C++ panel. Today, we've got 5 panelists here, all members of the C++ Standard Committee and experts in CUDA C++, to talk about what's going on in Standard C++, the latest developments, going into the next few standards, and also to talk about the future of CUDA C++. So let me first start off by introducing our panelists. I'm Bryce Lelbach. I have been on the C++ committee for about 7 years now. I chair the Standard C++ Library Evolution Group, and I'm also the chair for the US Programming Languages Committee. At NVIDIA, I'm an HPC Programming Models architect. I work with our HPC compiler team, our C++ core libraries team, and a few other teams to help set the direction for the things that they work on. And next, let me introduce Daisy Holman. Daisy, you want to tell the folks about yourself?
Hi, my name is Daisy Holman. I work at Google on programming model design and programming languages. I work on C++ quite a bit. I work on lots of different things, API design at Google. Yeah, I used to work in high performance computing with Christian, among other people. And I'm at Sandia, so I have that as my background. And I've worked on a bunch of different stuff with the standard. MD-SPAN is one of them, linear algebra, executors.
And our next panelist is Eric Niebler.
Yeah, hi there. I'm Eric Niebler. I am currently employed at NVIDIA. I work as tech lead of the C++ libraries team. I've been on the C++ committee for 20 years, which seems like a really long time. And in that time, I've done a few things. Most recently, what became Stood Ranges in C++ 20 is an effort I spearheaded. And I put together the team of people that created the sender-receiver executor proposal. And so currently working on that here at NVIDIA. It's very exciting work. Yeah, and that's about it. Yeah.
Next, we have Christian.
Hey, I'm Christian Trott. I'm working at Sandia National Laboratories, where I lead a team which develops COCOS, the performance portable programming model we are using within DOE and beyond in high performance computing mostly. And at the same time, I'm also on the C++ standard committee, have been there for about 5 years or so. And I currently lead the effort to get MD-SPAN into the standard, as well as I'm involved in standardizing linear algebra into C++.
Finally, we have Michael Garland.
Hi, I'm Michael Garland. I lead our programming systems and applications research group here at NVIDIA. I joined the company just before we released CUDA. And so during my entire time here, I've been interested in the question of what kinds of tools and techniques do we need to develop so that people can write parallel programs and run them efficiently on our platform. And adding parallel support to C++ has naturally been one of the things of great interest to me because it's something that directly impacts the ability of a lot of programmers to write parallel programs.
All right, great. So let's start off with our first question, which is, what upcoming standard C++ features are you most excited about? And let's start with Daisy.
Yeah, this is one of the ones I didn't actually have an answer written down for. I mean, I think the easiest one to talk about is reflection. I think there's a slide later on that, and it's still got quite some time. I am very excited about MD-SPAN, despite being in a position that I'm no longer really using it at my day-to-day kind of work. I think it is long overdue in standard C++, and I think it is a good example of how modern C++ design can isolate kind of the over-engineered maybe part of something that's still necessary for certain people from the simple interface that other users may need that doesn't need the complex parts. So I'm really excited to see that kind of design finally getting into, not finally, there's other parts of C++ that do that, but getting into C++. So MD-span is probably the near-term one, but reflection, I think, is going to completely change the way that we program in C++ once we finally get it. So I'm very excited about that, especially if we actually get reflection and generative metaprogramming.
So for those who may not know what reflection is, what is reflection, at least in the context of C++?
It's the ability to look at abstractions and constructs within the language and use those to make things, right? And that's really changed the way programming paradigms have evolved in so many other languages. Languages that have strong reflection support have much richer and kind of stronger patterns for separating concerns and for injecting dependencies and interacting various separate pieces of code with each other. And so I'm very excited to see how those patterns develop in C++.
Awesome. Thanks, Daisy. Eric, why don't we have you go next?
Oh gosh, it's so hard to pick just one. I'm mostly a libraries person, so it's library stuff that excites me. On the language side, though, I'd say that the thing that excites me most is something that we've already got, at least in C++20, which is coroutines. I am excited because that brings structured concurrency, like native support for structured concurrency into C++. And that is going to be a tremendous thing, right? Coroutines haven't broken big over the C++ community yet, but I expect it will, especially once we get more library support in the standard library. On the library side, C++23 is coming with a whole lot of new ranges goodies that have me very excited. Ranges, we got initial support for ranges in C++20. I worked on that for a long time, but really what came in 20 was the tip of the iceberg. Since then, a bunch of committee members have picked up the torch and run with it. And we're getting a lot of new range adapters in C++20. Very, very powerful programming paradigm, composable programming paradigm. And then looking a little farther out, very excited by the executors' work. I can't wait to see what people are going to do with standard executors. I'm looking forward to actually accelerating people's CUDA code using standard C++. I'm looking forward to getting coroutines running on the GPU. Can't wait to find out what people are going to do with that. So yeah, I mean, there's really a lot to look forward to and a lot to get excited about.
Thanks. Christian, what about you?
Yeah, so I mean, Daisy and Eric already had a lot of things, which come to my mind as well, right? Obviously, I'm super excited about MD-span, considering that my last 10 years were, largely designed around writing abstraction exactly like that. I'm also excited, about more parallelism, right? Also, in particular, what actually not really standard C++, right? What you guys are doing in CUDA, where you allow parallel algorithms to map to GPUs, that's super exciting. Coroutines, etc. Right? There's a couple other things actually, which aren't really upcoming for in the strong sense of the word, right? But upcoming for me, considering that I'm still restricted from I can't even require C++ 17 right yet based on my customers' requirements. So there is actually just the constructor template argument deduction is something I'm looking really forward to, because I'm getting the approval this year to go to C++ 17. And then just in 20, which is kind of getting fully implemented now in compilers, like the atomic graph, for example, is a big deal for us, right? I mean, the amount of time we spend to implement atomics for our things are like insane. And then another thing I discovered while writing more code with MDSpan for the reference implementation is the absolutely astonishing helpfulness of the requires clause. It makes writing, restricted code so much easier. The amount of SFINE-based magic we had to write before we had the requires clause was just tragic, right? And it's so much easier to write this kind of generic code with requires. It's unbelievable. So I'm really excited about starting to be able to use that in maybe 3 years or so.
And Michael, how about you?
I'm not sure I have any features at all to add to what people have already mentioned, but I'll emphasize a couple. I think I'm compelled to say that the thing I'm most interested about upcoming is executors, also known as senders and receivers, because it's something I've wanted in general for years at this point. The ability to control where something is going to run and how it's going to run is really essential for writing high performance and accelerated programs. Moreover, the current state of that proposal, much like our own CUDA graphs support on our own platform, is something that lets you describe an entire assembly of work that needs to be performed as part of some computation and then run it. And the ability to build up that kind of description and not simply talk about one parallel section at a time, I think will be very valuable in the long run. The other two I would briefly name check are ranges. I've wanted to be able to write code like that forever, and not having something in the standard library to kind of codify how that works was painful. And recognizing that multidimensional arrays are an actual data type is something else I look forward to in the standard library.
And I'll answer for myself, and I actually have two that have not been mentioned. The first is the next generation of parallel algorithms, which I think will be range-based and, most importantly, asynchronous. In C++ 17, we added parallel versions of the existing sequence algorithms in C++. And they're great. They're really powerful. It's very similar to the thrust library that Eric and I work on. But one of its big downsides is that all of the invocations of these algorithms are synchronous. You do a reduction, it launches the reduction, and then it gets the result and it gives you back to you. And then you go do a for each and it launches it again. You got to wait for it to complete, and then it comes back to you with the result. Well, these days, most of the times that we're doing parallel programming, we want to launch our work asynchronously and build up these computational graphs. And so senders and receivers will give us in C++ a framework for asynchrony and a language for expressing these asynchronous computations. And then on top of that, we'll be able to build asynchronous versions of the parallel algorithms. And I think that's going to be very powerful for users, because I've seen, even just with synchronous parallel algorithms, how much you can build. And the second feature I'll mention is I don't think it's as exciting as everything else that's perhaps been mentioned, but I think it is equally important, and that is the addition of extended floating point types that's going into C++ 23. We are increasingly seeing more and more of these new floating point types, mainly driven by the needs from the machine learning world, things like FP16, et cetera. And we've not had a way to express them as built-in language types in C++ until now. And it's very painful having to deal with these floating point types when you don't have an actual built-in data type for them. So I'm very excited for all of the pain that will be alleviated once we finally have those in all of our compilers.
As someone who just helped write code which wraps portably half precision types across different vendors, I have to say that is very true. just the CUDA half type is already painful enough if you want to try and make it work on both GPU and CPU side at the same time.
Yeah, and I mean, and that's one of the great things about, you know, extended floating point types is that we'll be able to just get rid of that CUDA half type at some point in the future and just replace it with a built-in, you know, language type. All right, let's move on to our next question, which is a loaded one. Why should standard C++ care about accelerated computing? And why should accelerated computing care about standard C++? Who wants to go first?
I have a super hot take on this one that might start some conversation.
All right, have at it.
And I mean, like, this is a little bit of a strong statement, but I don't think it's far off. I think increasingly accelerators aren't really programmed with programming languages. And I think that NVIDIA, the CUDA team, in general, outside of scientific computing, I think scientific computing, I see, especially HPC, that has to use these large supercomputers that are general purpose. I think outside of that, I see less and less use of general purpose programming languages for accelerators. And I think that's a really interesting monkey wrench in this question. And how does that apply? What does that affect? What effect does that have on HPC when you start to be the only users of something like Fortran? How does that cause the ecosystem to evolve? I don't think we're nearly at the point where the only users are HPC, but I think that in many ways we are evolving in a direction where people don't use programming, general purpose programming languages for accelerators.
Okay.
Go ahead, Christian.
Let me start by, and I think we jumped a bit too far, right? With Daisy's statement should have come a bit later. So why do we care about accelerated computing at all, right? And largely we care because more and more of all computing is accelerated, right? I mean, if we look at the high performance computing landscape, right, almost every computer is now not just CPUs, right, but has GPUs in it or potentially other things in the future, right? We're using FPGA, you know, there's people who are using FPGAs and so on. Our cell phones have, you know, tons of accelerators, which Daisy was kind of referring to, which aren't really general purpose, but accelerate specific things, right? So more and more computing is accelerated, right? There is, and that's why C++ needs to care about it, right? Because I mean, if we are only relevant for less and less of the computing hardware available, then that's a bad thing, right? Now, the thing is, from my perspective, and I've been thinking a lot about special purpose accelerators lately, right? Because even in HPC, we believe that is part of where we are going. And even if we go there, right, the point is that special purpose accelerators still need to interact with the whole entirety of the rest of our code, right? And so being able to program that from one language, which everybody kind of knows, right, is a really powerful helping thing, right? What I'm thinking there is that these special purpose things is something we need to bind into the library, right? Is there stuff in the C++ standard which can be directly mapped to these accelerators? For example, like the proposed linear algebra stuff, right? And this is, I think, where we need to figure out how to make that work, right?
Michael, I think you wanted to go next.
Yeah, I'll go next. So I think Daisy is quite correct that you see an increasing number of processors that are accelerators and that one does not program with standard or mainstream languages. But where I would disagree is that I don't think that represents an evolution. It represents a proliferation of a separate category of thing. Because there are basically two kinds of accelerators, right? There are accelerators that accelerate a particular API, much like hardware widgets on an SoC that automatically decode JPEG images or automatically encode video streams or things of that nature. And there are accelerators that accelerate programs that run code that users write. And I think those are two important but separate categories of processors, and that you would actually expect to see both. As we do right now on SoC processors, right? You have both processors that run programs, and you have blocks that do special things like encode JPEG or what have you. And for things like fixed file formats, where there's a very specific computation that needs to be performed by everyone, fixed function hardware even is great, and you can expose that as essentially an API accelerator. But then there's a much broader range of things where you really need to be able to run programs, and for that, you want to be able to author them in a mainstream language, which is why C++ should care about accelerated computing and vice versa.
Eric, you have any thoughts on this?
Yeah, for sure. So, I mean, Christian hit the nail on the head. Like, why should C++ care about accelerated computing? Because computing is accelerated. You know, C++ is the low-level programming language, the high-performance programming language, something that's supposed to get you right down to the metal. And look, without being able to target accelerators, we're only able to target maybe 1% of the average computer's compute power, which is embarrassing. So, of course, C++ needs to care about this. It's life or death. It will not be relevant if it can't. And why should accelerated computing and HPC care about standard C++? Well, it's all about that base, right? The installed base of C++ is enormous, right? There are a lot of people who know how to program C++. There are a lot of tool sets. I mean, you know, there's a C++ compiler available for every tiny little chip, hardware, whatever, right? You could imagine. There's compilers that will target that hardware and that platform that are the C++ compilers. So C++, if we can beat C++ into a shape such that it works for accelerated computing, then I think doing your accelerated computing in C++ is a no-brainer.
Daisy?
Yeah, I think I agree with all of these things. And obviously I made a strong statement to stimulate some discussion. I think that there are, so the first comment that I'd like to make on that is that I think that the real crisis for C++ in this is, we mentioned over and over and over again, API accelerators and wrapping things that go to API accelerators, right, as part of standard C++. And the problem is that these sorts of API accelerators that are fixed, and it's not just fixed for things like JPEG, right? It's fixed for things like the entire domain of machine learning, right? I think a lot of that is starting to be programmed with things that don't really map well to C++. I think that the crisis there is that no one cares that much about performance at that high level of abstraction. It's why we have such a proliferation of Python for those sorts of API accelerators. And I think that that is something that C++ has to take a step back and think about. What is our long-term purpose? Do we want to invest a lot into accelerated computing or continue doing what we do well, which is general purpose programming language for very high performance situations? I don't have an answer to that. I think the other part is that C++, because it is so particular about certain aspects of performance compared to more restricted languages, right, which it has had to be over the years in order to meet performance needs of the language, I think often ends up, when it's written on accelerators, ends up in a place where you have this awkward subset of the language that you have to keep in mind as not working. And I think that that is potentially dangerous and potentially square peg into round hole situation that we want to keep in mind. Like, I don't think C++ is going away for accelerators, but I think that we want to be very careful about square peg round hole situations, and not be closed-minded to the possibility that C++ is not the right tool for certain accelerators. I think GPUs are not there yet, but I don't know that they necessarily will always not be there.
Anybody have any responses for that?
Absolutely. Our plans at NVIDIA are that you can run all C++ natively on a GPU, and like all of it. We'll get there eventually. You'll have coroutines, you'll have exceptions, you'll have all of it. Yeah.
The first RFE on the NVIDIA C++ standard library requested that we support std cout on the GPU. And one day I would like to close that issue and not with a will not implement. So we've all said that parallel and accelerated computing is kind of becoming mainstream. Is HPC becoming mainstream?
It depends, I would say, right? I mean, as one of the people who is primarily in HPC right here, part of it is it definitely becomes more prevalent, right? I think this whole digital design, for example, makes a lot more industrial customers start to use HPC, right? In a way how like the government has been using it for decades, right? The question is, do you count things like machine learning as HPC? And I think it's probably a bit of its own thing, right? And so a lot of that kind of computing is probably not HPC. And in the classical sense, I think HPC is the thing where you try to solve kind of one monolithic or at least, reasonably large connected problem, right? Versus I think a lot of other people who need, high performance computing in just the general sense, they don't really need the whole system connected super tightly, right? They may need, a GPU and stuff like that, right? But they might need to talk with 1,000 GPUs to each other really, really fast. So I think there's still a difference there. But there's a lot of overlap on what happens on the specific hardware socket, right? I think that's where HPC and other types of, high-performing computing or computing where you need a lot of performance actually start to have a lot more overlap. Everything becomes parallel computing, right? In that sense, which was before a domain of HPC in its own, right? But now everything is essentially doing parallel computing, right? To some degree.
That's sort of the perfect lead-in for the next question that I have, which is, should standard C++ be extended to support distributed computing? Today, C++ has a flat view of memory. There's only this one process. And we've talked over the years, there have been proposals over the years, but it's never really been something that's been seriously pursued. There are other standard languages like Fortran that have a model for distributed computing. So is that something we should do for standard C++?
If nobody else wants to go, right, I'll have an opinion on that. So there is different parts to distributed computing in my mind, right? In some sense, you can see parts of the problem of distributed computing already just within a single node nowadays, right? Because you have different physical memory spaces with different characteristics. And if you try to treat it all as a flat space, you run into a lot of performance issues and potentially even, it's actually also easy to make correctness issues there, right? And so part of that already is distributed even in a much smaller sense, right? But I think, we have been working on putting I/O in right here, networking into C++, right? Which is arguably, a step in the direction of distributed computing, right? You talk to things which are outside of your computer, right? And I think it is something we can consider. How widely useful it is, I'm not sure. If we go that direction, I believe that the Fortran direction of essentially co-arrays is probably the most natural way of adding something.
So you want co-array C++. That's an interesting take. Daisy, it looks like you had some excited thoughts on this, maybe.
Yeah, I mean, I think my thoughts are not exactly secret to anyone in this room, and they align pretty well with Christian, although I wouldn't go nearly as far as saying co-array C++ is the right way to go. I think that memory space pointer annotations and memory space reference annotations, very similar to the kinds of, extensions that have been proposed for the past 20 years to various languages, are the direction that we want to go with that eventually, even if it does lead to this combinatorial explosion that's not really reasonable for compiler implementers. I think there's some discussion to be had here about whether C++ is the right language for this. I think it's possible C++ doesn't make enough simplifying assumptions for it to ever be reasonable to have multiple memory spaces, right? Like, you're going to have to make simplifying assumptions in some other part of the language if you want to avoid combinatorial explosion in this space. And I don't know that C++ is willing to, right? I think that it's possible that anything we would design for the purposes of HPC in this space and distributed computing in general in this space would add too much complexity to a language that already refuses to make simplifying assumptions in other spaces. And that may mean that C++ becomes less relevant for those domains, but I think that remains to be seen. I think obviously people on this particular call are making a pretty big bet that that's not going to be the case because we're all here, right? But I think it's possible that there are languages where it is reasonable to describe multiple disjoint or partially disjoint memory spaces depending on the level of complexity you want to add. But I think those languages would have to make some simplifying assumptions in places that C++ is not willing to make those assumptions.
Library guy here. I think the real question is, what is the programming model that lets us target all of this variety in hardware? What excites me is finding that programming model, finding a programming model that can scale from an embedded chip that can do just one thread, all the way up to these super clusters with thousands of CPUs and GPUs. Is there a programming model that can scale like that? And then, what are the runtime requirements? Certainly, you need some runtime that's capable of discovering your network layout and is able to shuffle resources around and maybe do smart caching in order to hide the fact that there's all these different memory spaces. And then also, your programming model will need to be expressive enough so programmers can have control over, I happen to know that things are going to be slow if I access one node from another node. So, how can I write my code in a smarter sort of way? Like, how can I get a programming model that is expressive enough to let me do that? I don't know that we need to extend the C++ programming language at all. I think we just need to think harder about programming model.
Interesting.
So I'll add a couple things in a slightly different direction. I would like to see people look at the language from the perspective of what aspects of its design stand in the way of supporting distributed computing, which is a useful thing to consider in contrast to other languages that have been more successful in the cloud. An example of the sort of thing I mean is that I believe it is the case that there is really no way to portably serialize and transport a closure in C++. An object which, now that we have lambdas, is more and more ubiquitous in people's code. There are various other languages, many of them based on the JVM, for example, or something like Python, where it's relatively trivial to serialize a closure and transport it to any other process running the same version of the language. Because of that fact, it was very easy for people, graduate students on their own even, to build fairly sophisticated cloud systems in those languages that could do very impressive distributed computations, which in C++ would be much more difficult. So while I am by nature very interested in the programming model questions that Eric brought up, I think it's also important to think about what are the aspects of the language that make it unnecessarily hard. And I think there's at least one of them, the closure issue. I think there are more related to some of the memory model issues and so forth. But I don't think we've really grappled with that in the language design.
Well, I think it's interesting that, we talked a little bit about reflection at the start of this. The introduction of reflection to the language might make it a lot easier for us to come up with standard ways of serializing things like lambdas.
Perhaps, and someone should certainly look at that,
Yeah. I would argue that's, I think, one of the key use cases for reflection. So I think sorry, go ahead.
Yeah, I wanted to say something as well. So I think there's two aspects to that, right? One is to this whole question of distributed computing, right? Whereas this upcoming stuff, we haven't really used in HPC much, right? Where you actually, move around closures, right? Where you move around compute from process to process. That's not actually how most of HPC right now works, right? Most of HPC right now, in terms of what it does with distributing things, needs to just think about where is data and how do I get to it, right? How do I get the data I need? So most of what the current crop of HPC computing does, right? It just needs to reason about how is my memory distributed, right? It doesn't actually do much in terms of distributing computing so much, right? All the computing is local. And I think that step is significantly easier than figuring out, how to make something like some of these task models, Legion or whatnot, part of the standard, right? Where you have to serialize computing as well. Because I think we can embed an expression of distributed computing in C++ just through the library, right? By essentially, I've been thinking about it in terms of MD span, right? If we have accessors there which say, I'm actually representing some distributed array, and the only thing you're ever going to get back from me is some reference handle, which actually isn't, which you can't use to get like an address of the actual underlying element for, right? Then that abstracts all the stuff in distributed computing from the data distribution side, enough away from the language that you're not allowed to do any of the language features which don't work with that kind of stuff, right? So I think it would be possible now without language change, as with core language changes, right, to support the distributed memory part of distributed computing. I think that would be feasible.
So I think Christian sort of has gotten to the discussion I really wanted to get to with this question, which is, of course, there's many different paradigms in the space of distributed computing, from something that's message passing to something that's, some sort of co-array model, to these task-based models. And I think that many of us probably thought about one or two of those particular paradigms when looking at this question. And I think it's actually probably valuable for us to be exploring whether we can and should standardize all of these. I think that the future will increasingly be distributed. And one other thing I want to dig into a little bit more is we talked a little bit about even within a single node or a single process, the need for some hierarchical view of memory. And I think coming with that is some model for discovering topology and making decisions based on it. And I bring this up because I know that Michael has some has some thoughts on what this should look like.
You're asking for my thoughts on what again? How to reason about placing stuff?
Yeah.
Well, there's more than one answer, right? Because there's more than one need that people have. But I think you need to start with providing low-level mechanisms that people can use to explicitly control where things are placed. Because I think that's what will enable people who understand how the system actually works to develop the kind of libraries that other people can use more productively. So giving people the ability to explicitly control where work is going to be launched or where data is going to be allocated is something that I think we need to be thinking about in the context of high performance systems. And of course, it is something that people do. And if you look at some of the HPC codes that people write in MPI, they use various libraries to traverse the NUMA topology of their nodes to figure out where to put data and the affinity between NUMA sockets and different NICs in the node and things of that nature. But none of that is something that you can really reason about in the C++ standard library at the moment. But we do have the beginnings of things that start to look like objects that represent where something might be placed, right? Obviously, allocators in some sense are an object in the program that indicates where and how memory can be allocated. Not a complete solution to that problem, of course, but they represent that idea. Executors are a thing that lets you represent where you want to execute something, right? Pushing that further ahead is something that I think we need to be thinking about.
Christian, Daisy, any thoughts?
Yeah, I think that, I just wanted to agree, first of all, with Eric earlier. I would call myself a library person also, and I think that there are some fantastic library solutions to these problems, and library is definitely a part of the discussion. I think the nuance to that needs to be, that I've learned, at least since doing more work on compilers, is that I think that it can't be the only solution here. I think that when you have very performance sensitive contexts where memory spaces are disjoint, there needs to be a way for the compiler to reason about that. And there needs to be a way for the optimizer to reason about that. And you can't just use flat memory space pointers. And either that involves teaching the compiler and the optimizer to reason about library constructs, which is a thing that we have done and can do and have done in the past, but it's actually, a lot more complicated than having some basic language building block that the compiler and the optimizer can reason about, right? And it's an important spot where there's loss of information in very performance sensitive contexts. And I think that giving the tools for library constructs to communicate information to the compiler is important. Whether or not those constructs are really ever exposed to an end user or anyone more than just a very heavy library developer, they need to be there, right? There needs to be a way to communicate things to the compiler. And the ways that we have to communicate things to the compiler along those lines currently are pretty rough. We're doing lots of reverse engineering to get these things working. And so that's the caveat that I would say to I still consider myself a library person, even if I do work on compilers from time to time now. And I just think that we're running way up past the edge of what we should be doing with libraries sometimes.
Yeah, so Daisy, I agree there, right? I think what we need is we need a way of, we already have ways in libraries, right, to express attributes our users can reason about, right? And our users can use to partially specialize, right? You look at the types and you partially specialize and do something different depending on the type, right? What we need is a way for some of these attributes to be actually communicated down to the compiler, right? And so I'm thinking about things like, which we don't really have in C++ right now, but restrict, right? The restrict keyword on a thing. I can make an attribute restrict for my MD span, right? make it an accessor which says that, and in principle that communicates to the user the semantic. This thing is not allowed to be aliasing in the context of where this thing lives, right? But I don't have a way of telling the compiler that. If I had that attribute which is part of the language, right, and also changes the type of my pointer, right, then I can combine these things, right? And there are things like that, things like the memory space, right? If I make the memory space not just a specific type tag, but I can actually express it as an attribute on the pointer, so the compiler can reason about, oh, this is, I don't know actually how that what these things are, but I think there are address spaces in LLVM, right? So if we can then connect, a type on the library level to an attribute, which the compiler understands, I think that is ways, how we could make this possible, right? And I really want to explore that a bit more with proposals in the C++ standard.
I believe those are OpenCL address space or memory space annotations, if I'm not mistaken. But yeah,
right,
that is exactly what I was hinting at earlier.
Yeah, but they've been reusing them in, for example, OpenMP and in HIP and whatnot, right? As for the different front end languages.
Yeah, and there is a notion of address spaces in LLVM too, of course. So, Christian, do you imagine these attributes that you'd want to pass through to compilers? Do you imagine if we were to standardize them that we would standardize each one individually as a magical library construct, or do you imagine some sort of generalized facility for passing information tags like this to your compiler?
I actually think I think of it more as generalized information, and in some sense along the lines of the volatile and constness, right? We already have a way of having a base type for pointers, right? Which we then extend with, it's const, it's volatile, or it's const and volatile and stuff. We have facilities to remove these attributes from that base class, right? Or that base type. And I think we could build something which builds on top of that, right? Which makes that more general.
Interesting. Somebody else have any thoughts on that?
I mean, this is where what I was saying before comes in, is that I think that C++ is not willing to make simplifying assumptions in other places that we would need to make that viable. I think I've had this discussion with compiler people before, and they basically say that already with const, volatile, and restrict, which since most of them both support C and C++, they have to track all three of those, right? Even with CVR qualifiers, the exponential explosion of possibilities is too much. If you were to add a fourth thing to that is actually orthogonal to those three things, or a fifth thing, then it would just be completely not viable with the way that C++ works. This is what I've been told, at least by compiler implementers. I am not sure that I buy it myself, but I do think that we have to be careful about that. And that's what I was getting at with these simplifying assumptions, right? Are we going to have arbitrary sets of qualifiers on member functions and pointers, right? Because the way that C++ builds on itself, you end up with that kind of thing, right? I think deducing this helps us a little bit with that, but I think it starts to get out of hand pretty quickly.
So I think this is actually a common problem that any sort of property system runs into, where if it's a closed set and it's not generalized, then adding things to that closed set can often lead you to this Cartesian product of all of the options. But if it's a system that's designed from the ground up to support open sets of attributes, then you can often avoid having to have that Cartesian product handled in every case, because instead, in every place where you're dealing with these attributes, you assume that you've just got a collection of them. And so perhaps yes, it would be challenging to add a fourth, on top of const, volatile, and restrict, but maybe we could do it in such a way that we'd never have to add a fifth, because the fourth would be generalized. But let's move on to what I think maybe our last question. which is, what will or what should the relationship between CUDA C++ and standard C++ be in the future? I'm gonna ask, I think, Michael to start on this one.
I'll try and be brief. I think in the future, standard C++ will embrace ever more parallel computing capabilities. And I think that languages like CUDA C++ are sort of demonstrating the way in which those kinds of ideas can be embedded in a C++ based language. I also think that CUDA C++ will be the best way of implementing C++ libraries on NVIDIA platforms, of course, because that's its reason for existence in some sense. I think that, well, I'll leave it at that since we're short on time and give other people a chance to respond.
I'll go next. Yeah. So I believe standard C++ is going to get more and more powerful and more capable on accelerators and in GPUs in particular. And to a certain extent, it's going to be eating CUDA's lunch at the very low end. That is, people who don't have like strict performance requirements will be able to just write standard C++ and get reasonable performance from their GPUs, reasonable acceleration. I think CUDA C++, that the C API that is CUDA, and the Chevron syntax, like I think that's always going to be there, and it's going to be there for the real gearheads and the performance freaks and the bit twiddlers who are going to want to squeeze every ounce of performance out of their expensive hardware. So that I think CUDA C++ is always going to be there for those people.
And it's not just about the, it's not just like an entire application falls into that low end versus the high end. It might be the case that 80% of your code, is not performance critical and standard C++ is sufficient, and that there's 20% where you need to, really write CUDA C++ and use the extensions to get peak performance.
Precisely, right? And with a powerful enough standard C++ that's capable of it being accelerated, then you get to write your application in standard C++ and then benchmark and find out where actually are the hotspots and where do I need to rewrite things in CUDA.
I don't even think that it's that much about performance, right? Because I think if you have a powerful enough, parallel expressions in C++ itself, the number of cases where you need to go to lower level is actually going to be fairly limited. But what you need CUDA C++ still for is expressing those things, right? Also, it's the target for mapping the C++ expressions to, because CUDA C++, right, is a fairly one-to-one expression of what the hardware actually does in some ways, right? It's very tightly coupled to the hardware. In some sense, I see CUDA C++ as the assembly, right, for the GPU. And what you need that as a target, what you map the more general expressions to.
Daisy, any thoughts on this?
I think that we are back to a spot where the more in this discussion where we have to ask, are these more general kind of get something working, low-end expressions, low-end uses, better targeted by other languages, right? Is like, do we want to put a huge amount of effort into building what effectively end up being API accelerator wrappers into standard C++, or do we want to focus on making standard C++ be better at expressing those kind of low-level bit twiddler things and allow higher-level languages that are better designed for it to focus on the API wrapping and the high-level calls to do the things that Eric kind of described at the very beginning of his answer to this question, which is to get something working without having to do lots of bit twiddling. I think there's space for both of those things. I think just because someone's using C++ doesn't mean that it's only because they want things that are super fast and otherwise they would be using Python. I think people use C++ sometimes because they don't know Python, right? I mean, like, that is a thing that happens. We have to, like, as language experts, we have to admit that sometimes people learn one language and they use it for the rest of their career and that's it. And that's fine. That is totally a reasonable thing to do. And we need wrappers and bindings in C++ for those kinds of things. And I think that to some extent that's what Eric is talking about. But the other side of that is that I think that C++ is going to get overshadowed in that space by languages that are more user-friendly and make simplifying assumptions in exchange for performance that we are asking standard C++ to make in order to accommodate those parts of GPU programming.
All right. Well, I want to thank all of our panelists for what I think was a really excellent discussion today. And for everybody who's listening in the audience, if you have questions, you can put them in the chat and we'll be able to answer them live.